Please visit website mmsprogramsville.com for all the education videos. Now we will see design of T-beams, right? That is flange beams. Introduction. When a reinforced concrete slab resting over a concrete beam is casted together, they act as one unit. The concrete in the slab, which is on the compression side of the beam, will resist the compression force, and the tensile force will be taken by the steel in the tension side of the beam. This combined slab and beam uh, unites these combined slab and beam units are called as flange beam, as shown in figure below, right? This is a slab. Okay, this is the center of the slab, this is center of the slab. Okay, this is b1, this is b, this is b1. So this will give an L beam effect, this will give an T beam effect, and this will give an L beam effect, right? So we can see over here that the stress, compressive stress, is maximum at the midspan and minimum at the edges, and this is not uniform, right? So the course suggests to take an uniform stress. So you have to take an imaginary effective width, flange width, right? So it has to be taken in such a way that whatever the force due to this stress diagram we get should be equal to the force that we get from this stress diagram, right? Okay, so this is a T-beam. So this is known as flange, and the bottom portion is known as web. Okay, and this is the transverse reinforcement which has to be tied properly with that of the web reinforcement to give an to make the slab and beam act integrally, right? So and they have to be casted together. The joint has to be monolithic, right? Okay. One should understand that T-beam and L-beam are uh, obtained when there is sagging in the beam. Okay, so that the flange is under compression. Okay, one should understand that T-beam and L-beam action are obtained when there is sagging in the beam, so that the flange is under compression. As shown in figure below, some portion of beam near the support may be found under hogging. In this region, the concrete in flange will be under tension, which where the concrete is neglected, right? And will act as singly or doubly reinforced rectangular section, right? So this is your continuous beam with edges fixed. We can see at support there are hogging moment, and in between we have sagging moment, right? So near the support, there is tension on the top due to hogging, so the flange will be under tension, and we know that concrete in tension is neglected. That is why in this region and in this region, the section will be designed as a rectangular section, right? Whereas in between this, there is sagging, so the tension is at bottom, and at top, the flange is under compression, right? So that is why in this region you will get a T-beam action. In case of simply supported beam, the whole beam is under sagging and T-beam action is available along the whole T-beam, right? So this is a simply supported beam. Okay, we can see, and this is under sagging, right? So the flange is under compression along the whole beam, right? So that is why you will get a T-beam action along the whole beam, right? Okay. General criteria for flange beams. A slab acting as a compression flange of flange beam shall satisfy the following conditions. The slab shall be cast integrally with web and provide transverse steel in the slab for integral action, see below. Okay, or the slab or the web and the slab shall be effectively bonded together by any other means. Okay, so this is these are our beams, and this is slab spanning in this direction. This beam we can design as a T-beam, okay. The main steel of the slab is in this direction, okay, and this main steel of the slab will act as transverse reinforcement for the T-beam, okay. They have to be tied properly with the web reinforcement so that you get a proper integral action, and they have to be casted together, okay. The joint between the slab and the beam should be monolithic, yeah, okay, so that you can get a proper T-beam action, okay. If the main reinforcement of the slab is parallel to the beam, transverse reinforcement shall be provided as shown in figure below, okay. Sometimes it so happens this is the beam which we want to design as a T-beam, okay, but our spanning of slab is in this direction, and in this direction we have distribution steel, okay. So to get a proper T-beam action, we have to provide additional transverse reinforcement as shown over here of a length less than equal to L by 4, okay, where L is from center to center over here as shown over here, okay. And this transverse reinforcement should be at least equal to or greater than 60% of the main steel of the slab that is provided at the mid span, okay. So this is very important, then only you can get a proper T-beam action in such cases. Effective flange width, okay. The actual compressive stress distribution is maximum at the center of the flange and minimum at the edge of the flange, as shown over here. Maximum at the midspan and minimum at the uh, edges, okay. The nature of this compressive stress distribution is very indeterminate. The code IS 456-2000 suggests to use an imaginary width of the flange over which a uniform compressive stress is assumed to act, okay. So we have to take an imaginary effective width of the flange, BF, okay, where the stress compressive stress distribution is uniform, okay. That is the code says. Okay, the following recommendations are given in the code IS 456-2000, clause 23.1.2 regarding the effective width of the flange can be considered and can be used safely for design. Okay, these are the T-beams and L-beams which are part of a slab. Okay, this is a part of a slab, this is part of a slab. Okay, for that you can take effective width B of a flange, that is BF, sorry, BF, okay, that is equal to L0 by 6. What is L0? L0 is the distance between the zero moment. In case of simply supported, moment is 0 over here, moment is 0 over here, so this is L0. In case of continuous beam, moment is 0 over here, moment is 0 over here, so this is L0, right? But for case of continuous beam, code has simplified the equation. Code says L0 in case of combined continuous beam can be taken as 0.7 times the effective span of the beam. So you just find the effective span of the beam and multiply it by 0.7, and that is what you can take it as L0, right? So BF for T beams, which are the part of the slab, okay, can be taken as L0 divided by 6 plus BW. BW is the width of the web plus 6 times the DF, where DF is the depth of the flange, right? Okay, but in no case your BF should be greater than B. Okay, BF cannot be greater than B. Okay, that is what the code says. So this is the formula for L beam, that BF is equal to L0 by 12 plus BW plus 3DF. Okay, if it is an isolated beam, okay, so it is, say the beam is individual and is not a part of any slab or any other structure, okay, it is say isolated. In that case, BF for T beam is should be taken as L0 divided by L0 by B plus 4 plus BW, okay, where B is the uh, actual flange width, right? Actual flange width, right? Fine. So similarly, this is the formula for L beam, okay? But in no case, your BF should not be greater than the actual width B, okay? So these are the notations which I explained, okay? Again, the same note which I just told you, that for continuous beam, and frames, L0 may be assumed to be 0.7 times the effective span of the beam. Okay, now action of under reinforced flange section. So there can be three cases. Okay, the cases of flange section, there can be three cases depending upon the flange depth and the depth of the neutral axis. Okay, flange depth, that is df, and depth of the neutral axis, that is xu. Okay, so first case is when the neutral axis lies inside the flange. Okay, that xu is less than df. Okay, xu is the depth of the neutral axis and df is the depth of the flange. So this is your T beam. Okay, so this is your df. This is the depth of neutral axis is xu, right? So if your neutral axis falls within the flange, that is your case 1, then it becomes a rectangular section case, because below the neutral axis the concrete is under tension, which is neglected. So this becomes a shear case of rectangular section, right? So everything remains the same. Only thing is, instead of B, we have to take the width of the flange, that is BF, right? So this is going to be your design stress diagram. This is your design stress diagram, which is applied to the whole width of the flange, that is BF, right? This is how you get the force C, right? So we know force C is 0.36 FCK. Instead of B, you will have to take BF, okay? Because this is acting on the whole flange, right? BF into XU. T, you know, it's simple 0.87 F5 into ASC. So everything remains the same. Even the lever arm remains the same as in case of rectangular section, that is D minus 0.416 XU. Okay, fine. So let us start with let us try to understand this clause. Okay, in most of the cases you will find that the neutral axis falls within the flange and the beam is designed as simple rectangular section, as the concrete on tension side below the neutral axis is neglected. Okay, as the flange have a large amount of concrete. Okay, so there are chances, there are 95% chances that the neutral axis will fall within the flange. Okay, and you will have to design as a rectangular section. Okay, uh, the only thing that is to be kept in mind is that the width of the beam to be taken in design will be equal to the width of flange. Okay, fine. So from equilibrium we know C has to be equal to T. This is C, this is T, we know, right? Everything, same thing is written over here. T is equal to C, we know T, we know C. The lever arm we know, that is D minus 0.416 XU. So you can find XU, this is T divided by C. Again, moment you can easily find. Moment is equal to C into this lever arm. This is C, this is lever arm, right? So that is moment C into lever arm. This is how we get the moment, right? When you uh, resisting moment of the section, right? So you can also find moment as T into lever arm. Okay, so T into lever arm. T, we know this is T, this is lever arm. So this is T, this is lever arm. Okay, and from this you can find AST. AST is equal to moment divided by stress in steel into lever arm. Once you know AST, you can find percentage of steel, that is 100 AST divided by BF into D. Okay, so we here only thing that is to be remembered is instead of B we have to take BF. Okay, okay. Now if this section is found to be uh, under reinforced, okay, then you can use this formula for finding the steel. Okay, this formula is applied to all the rectangular sections which are singly under reinforced section. Okay, so if the section which we design is found to be under reinforced section, in this case one, this is already we know that we have to consider this as a rectangular section, then this formula can be used for directly can be used for finding the steel. Okay, so now moving to the case 2, when the neutral axis lies within the web, that is depth of neutral axis is greater than df, xu is greater than df. Okay, but the strain point 002 lies within the flange. That is, we know that the strain 0.002 falls at a distance 3 by 7 XU from the outermost compression phase. Okay, and up till that distance, the stress is constant. After that, the parabolic portion starts, right? So you can also say that your XU is greater than DF and 3 by 7 XU is less than DF, okay? Or you can say your XU by DF is greater than 1 and less than 7 by 3. All the three cases are the same, right? So that is this case. Let us see the figure, okay? This is your T-beam, okay? Now we will divide this T-beam in two parts. This is flange, and this we will take as a rectangular section, right? So we have two stress diagrams, okay? One for this flange, that is this, one for the rectangular portion, that is this, right? Fine. So now our case 2 is, this is our neutral axis step, that is 3 xu by 7, okay? So this line, we have the strain 0.002. This is outermost strain, that 0.0035, but strain at the level of distance, that is 3 by 7 xu, will be 0.002, and up to this, okay, the stress is constant, that is rectangular. After that, the parabola starts, okay? So over here we can see that strain 0.002 falls within the flange, or you can also say that 3 by 7 xu is less than df, okay? So that is case 2. So in this case, we will have a rectangular stress diagram till here. Then after that, we will have a truncated portion, parabolic part of the parabolic stress diagram, right? So this is the stress diagram which will be acting on this flange, okay? But this stress diagram is little bit complicated. So code has given a simple solution that you can take an equivalent stress diagram like this. Okay. Instead of this, you can take an equivalent stress diagram like this, where the depth of the stress diagram has to be taken as YF, where YF will be equal to 0.15 XU. XU is the depth of the neutral axis. Okay. And uh, plus 0.65 DF. DF is the depth of the flange, right? So over here, the neutral axis falls in the web, but your strain 0.002 falls in the flange, right? That is the case 2, right? So this can be replaced by this. So now this is applied to the flange portion, and this is applied to the rectangular portion. So that is what is shown over here in this figure. You can see this is applied for the flange portion, okay? And this is applied for the rectangular portion, right? So it becomes very simple. What is C1? Force C1 can be found as 0.447 FCK into Fy. So that is the area of this rectangle into this length, right? So this is BF minus BW. That will be the length of the flange, right? This is BF. This is BF minus BW. So that will be the length of the flange, okay? So C1 force is equal to 0.447 FCK into Fy into BF minus BW, right? So that is what I have written over here, okay? C1 is equal to 0.447 FCK into Fy into BF minus BW, right? 0.447 FCK is this, YF is this, okay? Over here, please remember YF will be less than DF, okay? So that is C1 force, fine? Now YF code says we have to take as 0.15 XU plus 0.65 DF, and YF has to be less than DF, right? So from the figure we can see for equilibrium T has to be equal to C1 plus C, okay? C we know it is 0.362 FCK into BW, okay? This is BW into XU, okay? That is C. This is your lever arm, D minus 0.416 XU, and the lever arm for this will be, this is YF, okay? So this will fall at the center of YF, so this will be equal to D minus YF by 2, okay? So that is what is written over here. C1 is 0.447 FCK BF minus BW into YF. C is 0.362 FCK BW into XU. T is 0.87 FY into ST. We know C is equal to this, T is equal to C1 plus C. So C is equal to T minus C1. So this is C1, this is T, this is C1, this is C. You can find XU, or you can replace YF by this value, okay, and you can get a new equation like this, right? Okay, so that is the depth of neutral axis. Now moment of resistance, simple. You take C1 into lever arm plus C into lever arm, okay. C1 into lever arm. C1 we know, lever arm is this, that is this lever arm. C we know, into this lever arm, this is lever arm, this is lever arm, right? So that is how we get over here, okay. This is C1, this is lever arm, this is C, and this is the lever arm, right? So this is how you get the moment of resistance, okay. From equilibrium we know C is equal to T is equal to C1 plus C. So this is your T, this is your C1, this is your C, okay, okay. This is your T, this is your C1, this is your C. So EST can be found as C1 plus C divided by stress in tensile steel, okay. So this is your case 2. Now coming to case 3. When the neutral axis lies in the web, okay, that is XU is greater than DF, and strain point 002 also lies in the web, that is outside the flange, right? That means your XU is greater than DF, and 3 by 7 XU is also greater than DF, okay, because strain point 002 falls at a distance 3 by 7 XU. If your strain point 002 falls in the web, that means 3 by 7 XU is greater than DF. Simple, right? So let me show you, explain you in the figure, right? Everything remains the same. This is your T. Now over here, this is our 3 by 7 XU, right? So this line over here, this is the strain point 002, and this is in the web, right? That is outside the flange, okay. So when we know that up to this strain, or you can say up to this distance, we have a rectangular, that is uniform stress diagram, right? So that is why over here only thing that is going to change is YF will be equal to DF, okay. In case 2, YF was equal to 0.15 XU plus 0.65 DF, but not greater than DF. But over here, in this case, YF will be equal to DF, right? So this is the stress diagram in your flange, and this is the stress diagram for the rectangular section. Okay. So instead of YF, you will take DF. You will replace Y by DF. That is the only change. Okay. So simple. Again, C1 is equal to 0.447 FCK, okay. C1 is 0.447 FCK into YF. YF will be equal to DF, okay. And the here the lever arm will be D minus DF by 2, because YF is equal to DF, right? That's why, okay. So your C1 will be 0.447 FCK into YF into BF minus BW, okay. 0.447 FCK into YF into BF minus BW, where BF is equal to DF, okay. So we know T is equal to C1 plus C. C1 we know 0.447 FCK, BF minus BW into DF. C we know it is 0.362 FCK, BW into XU. T we know it is 0.87 F5 by 0.87 F5 AST. C is equal to T minus T1. This is T, this is my C1, this is your C. You can find XU. Moment you can take C1 into lever arm plus C into lever arm. Okay. C into lever arm plus C1 into lever arm. So C1 you know, lever arm you know, C you know, lever arm you know. So that is what I have kept over here. Okay, over here. This is C1, this is C1, this is lever arm, this is C, this is lever arm, right? So that is how you can find the moment of resistance. Now you can find the area of steel taking T is equal to C1 plus C. So T, this is T, 0.87 F5 into ST. C1 is 0.447 FCK into BF minus BW into DF. C is 0.362 FCK BW into XU. Okay. So EST can be found as C1 plus C divided by stress in steel. Okay. So this is your case 3, right? Now in case of T beams, you have to do the check for vertical deflection. Vertical deflection limits, as suggested by the code IS 456-2000, calculate clause 23.2.1, generally be assumed to be satisfied provided that the span to effective depth ratio are not greater than the values obtained below. Okay. So this is something which we know that up to the span 10 meters, the basic L by D ratio for cantilever is 7. For cantilever it is 7. For simply supported it is 20. For continuous it is 26. If the span is greater than 10 meters, then you have to multiply this by 10 by span. For cantilever, you have to do the rigorous calculations. Okay. But in case of flange beam, there is another reduction factor that you have to multiply with this, right? That is you have to take from this graph. That is, you first have to find the ratio of web width to the flange width. Web width is BW, flange width is BF, right? For that ratio, you have to find the reduction factor and you have to multiply with this, right? Other things are same. You can find KT for the known percentage of steel. Okay, first find the stress in steel, then for the corresponding PT you find the KT, that is modification factor corresponding to the percentage of tension reinforcement. Similarly, you can find KC, that is modification factor corresponding to the percentage of the compression steel, right? Now, limiting capacity of the T-beam. In case of balanced section, XU is equal to XU max. Find XU max using strain diagram. The above all the three cases, in above all three cases, replace XU by XU max, so that the value of MU max is obtained. That is limiting moment capacity of the section. Okay, so the above three cases which we study were for general. Okay, all the same three cases can also be repeated for a balanced section. Okay, only thing is that over there we used word XU. In case if the section is balanced section, then you have to, instead of XU, you have to take XU max. Okay, so everything remains the same, only that you have to do is you have to change from XU to XU max. Okay, so we know for XU, this is a table very known, very well known to us. XU limit by D ratio, so that is for FE 250, this is FE 4, FE 500, this is for FE 500, right? Okay, now minimum and maximum tension still required as per code. The minimum area of tension still required to be provided as per IS 456-2000 is calculated as on the width of the web of the T-beam. So this is the formula given in the code. Only thing is that instead of B, you have to change this to BW, where BW is the web width of the T-beam and D is the effect depth. The maximum area of tension steel limit that can be provided as per IS 456-2000 is calculated on the width of the web of the T-beam. Over here, that is 4 first, we know that AST maximum that is allowed is 4% of the cross section. Instead, over here we have to take BW. Okay, instead of B, you have to take BW into effective depth D. So BW is the web width of the T-beam and D is the effective depth. Okay. So doubly reinforced section, that is T-beam sections. Whenever the design moment exceeds the ultimate moment resisting capacity of the singly reinforced section MU limit, then the section has to be designed as doubly reinforced section. The basic fundamentals for design of doubly reinforced T-beam are the same as for a doubly reinforced rectangular section. Okay. It should be noted that as the area of the concrete in compression of a flange is quite large in case of T-beams of T-beam balance section, okay, as compared to the rectangular beam, the area of steel required for the balance section will be large as compared to the rectangular sections, right? For this reason, doubly reinforced T-beams are usually not used in practice. It is as advisable to increase the depth of the T-beam. Okay, this is very important. Okay, fine. Illustrative example. Now we will start with an example. Uh, First, we will do a analysis problem. Okay, calculate the ultimate moment of resistance for a D beam for the following data. We have BF is 1500. BF is 1500. We have DF as 100. DF is 100. Then overall depth is 600, and BW is 300. Okay, okay. FCK you have to take as 20. FI you have to take as 415. Okay. Now the area of tension reinforcement is given. Okay. In case 1, the AST is 220 and D1 is 40. So AST is 220 and D1 is 40. So effective depth, this is overall depth, that is 600. So overall depth minus D1. D1 is the effective cover for your tensile steel. This is D1, right? So this is D1, okay? So effective depth is D minus D1, that is your effective depth D, okay? So that is equal to, for case 1, when EST is 220 and D1 is 40. So effective depth is D minus D1, that is equal to 560. So in case of analysis of a T section, we have to make number of assumptions, right? So first we'll assume that the XU is falls within the flange, right? That XU is less than DF, right? So simple, we know C is equal to T. So this is T divided by C. Okay, we get XU is equal to 73.54. Now 73.54. DF is 100, right? So 73.54 is less than DF. So our assumption is correct. Okay, that means for sure the neutral axis neutral axis falls within the flange. Okay. So now next step is we have to check for XUmax. XUmax for Fe4 on 5 is 0.48D, as we know from the table above. This is the table for Fe4 on 5. XU limit by D is 0.48, so XU limit is equal to 0.48D, right? So this is what we are taking over here, because we are using Fe415 steel. So XU max is equal to 4.48D, that is equal to 268.8. Our XU is less than XU max, so the section is under reinforced. Okay. Now we know that the section is under reinforced, right? So we can find our moment of resistance simple by taking MUR is equal to C into lever arm. This is C, this is lever arm. So this is C, this is lever arm, and we get a moment of resistance as 420.47, right? Fine. So XU, which we found is 73.54. This is our XU. So this, our neutral axis falls within the flange. Okay, fine. So next is take AST as 4504 and your D1 is 65, right? So D1 is 65 and AST is 4504. So our effective depth will be 600 minus 65. So D effective depth D is D minus D1, that is 535. Again, take the same assumption that your XU is less than DF. Find XU. XU is 150.57, but our DF is 100, so it is greater than DF. So our this assumption is wrong. Okay. So now we will have to go for another assumption that 3 by 7 XU is greater than DF. Okay, this means that the strain 0.002 falls within the web, right? We are assuming that 3 by 7 XU is greater than DF, right? It is greater than DF, that is 0.002 strain falls in the web. Okay, this is our assumption. Now we will have to see whether this assumption is correct or not, right? So for this becomes our case 3. Okay, so for case 3, this was the formula XU which we found. Okay, let me show you. Let us go to case 3. Case 3, this is case 3, right? This is case 3. uh, Case 3, we found our XU, right? So I am using this same formula over there. Okay, so XU I have taken from here, and okay, this is the formula, right? So from this I got XU as 256.2, right? Now I have to check whether 3 by 7 XU is greater than DF or not. So putting XU over here, I am getting this as 109.8, which is greater than DF. So our assumption is correct, right? That means the strain 0.002 falls in the web, okay? And your 3 by 7 XU is greater than DF, right? So this is our case 3, right? We will have an uniform stress diagram on the flange where YF will be equal to DF, okay? And this is the stress diagram for this rectangular section, right? Okay. So first, the next step is we have to find XU max, that is 0.48D in case of Fe415. This is 256.8 and our is 256.2. So this is less than XU max. So our section is under reinforced. So okay, it's safe, right? Fine. So simple. Now you have to find the moment of resistance, that is C into this lever arm plus C1 into this lever arm. C, this is for C, this is what you know, 0.36 FCK BWXU into lever arm. C1 you know, it is 0.47 FCK into BF minus BW into DF divided by into this lever arm, right? So this is how I get my moment of resistance equal to 757.39 kilonewton meter, right? Now the third case, where AST is 3272 and D1 is 40. Okay, so this is the case. AST is 3272 and D1 is 40. Okay, so your effective depth will be 600 minus 40. So let us start with that. Okay, over here, effective depth D minus D1, that is 560. Okay, again take the same assumption. First, XU is less than DF, find XU. This is 109, which is greater than DF, so our assumption is wrong. Now again take the same next assumption, that 3 by 7 XU is greater than DF. Find your XU, then it is coming out to be 50.25. Now check 3 by 7 XU is greater than DF. 3 by 7 XU is found to be 21.54, which is less than DF. DF is 100. Again, this assumption is wrong. So the case is false in the case 2. Okay, so that means now the case is that 3 by 7 XU is less than DF, that is XU is greater than DF. Okay, the neutral axis falls in the web, but the strain 0.002 falls in the flange. Okay, that is case 2, right? So that is our case, right? So over here we will have to take YF is equal to 0.15 XU plus 0.6 DF, because and your YF has to be less than DF. Okay, so this is our second case, right? Simple, everything remains the same. Okay, so we know T is equal to C plus C1, right? So this is C1, 0.36 FCK BW into XU. This is C1, 0.447 FCK into BF minus BW into YF. And this is your T, okay? 0.87 FI AST. Now you can replace this YF by this value, okay, 0.15 XU plus 0.65 DF, right? So putting this value over here, you get this equation, right? Now solving this, we get XU is equal to 131.26, which is less than XU max, that is 0.48D. So our section is under reinforced. Okay, that's fine. Now once you know XU, you can find your YF. So YF is found to be, now XU is 131.26, right? So this is XU 131.26. Neutral axis falls in the web, right? But strain 0.002 falls in the flange. Okay, so once you find XU, you got your YF. Put the value of XU over here, you get YF is equal to 84.68. Okay, which is less than DF, so it's okay, right? Over here YF should be less than DF. So YF is found to be 84, which is less than 100, so that is okay, right? Now you can find the moment of resistance. Simple, C into lever arm, C1 into lever arm, right? So everything is known to us. This is for C, this is lever arm, this is for C1, this is lever arm. So you get moment of resistance equal to 471.35 kilonewton meter, right? Similarly, you can go for the next question, that is AST is 4638 and D1 is 65. So effective depth is 535. Again, try for the first case that XU is less than DF. So that is found to be 155, which is greater than DF. So the assumption is wrong. So again, assume that 3 by 7 XU is greater than DF. Find your XU. So XU is found to be 278.58. So we have to check 3 by 7 XU is greater than DF. So 3 by 7 XU is equal to 119.39, which is greater than 100 DF. So the assumption is correct. Now check that whether this is less than XU max. So XU max is 0.48D, that is equal to 256.8. So our XU is found to be greater than XU max. That means the section is over reinforced, which is not allowed, right? So either you will have to increase the depth of the T beam, or you will have to go for a doubly reinforced T beam section. Okay, simple. Over here, I have just calculated MUR uh, limit, that is assuming X is equal to XU max, right? So C into lever arm plus C1 into lever arm. This is how we get 757.8 is your MUR limit. Okay, that is moment of resistance of the balance section. Okay, okay. Now we will do. Okay, this is another very important figure. You can do the analysis of T section. You can make a computer program like this. Varying the percentage of steel, you can get the corresponding moment of resistance and the depth of the neutral axis. This is the graphical representation. This green graph shows the section is under reinforced. Red graph shows the section is over reinforced. And this junction shows the balance section. Detail of balance sections are shown over here. This is XU max, this is PT limit, this is MU limit, right? Now we can see over here that when the section is under reinforced, the graph of moment to the percentage of steel varies linearly. Okay, as you increase the percentage of steel, the moment carrying capacity also increases. But as the case at it becomes the over reinforced section, so we can see though you increase the percentage of limit, the moment carrying capacity does not increase. Okay, so this is very important, right? So W reinforced section in case of T beam, over reinforced section in case of T beam are very uneconomical, and so are the W reinforced T beam section, right? So it is always good to increase the depth and make the section under reinforced so that you can get an economical T beam section. Okay. So now we'll do a design problem. A T-beam, okay. Uh, a T-beam consists of a flange, okay. Flange BF is 1100, DF is 120. Effective depth D is given to us, that is 600. BW is 275. FY is 20, and FY is 415. Okay. So we have to find the moment of resist. We have to find the steel area for the given design moments. Okay. So first, let us start with the first case. Okay. When your design moment is 380 kilonewton meter, right? Over here also we have to do a number of assumptions, right? So in this case, first assumption is we will assume that XU is equal to DF. That means we are assuming that our neutral axis falls at the bottom of the flange, right? And we know for this is the rectangular section, so you can easily find the moment of resistance, that is equal to this is our stress diagram, right? So force C will be 0.36 FCK into BF, because this stress diagram is acting over the whole flange. Okay, that is 1100 mm, right? Into this effective into the lever arm, right? This is C into lever arm, right? So MUR1 is found to be 522.79. So this is very important to be remembered. When our neutral axis is at the bottom of at the bottom of the flange, then the moment of resistance of the section is found to be 522.79. Our design moment is 380, which is less than 522. That means our XU definitely falls within the flange. MU is less than MUR1, hence XU is less than DDF, right? So this is a case one. Okay. So once and this is case one, so we can use this formula assuming that the section is under reinforced, right? So we get steel as 1864.3. Now let us find the actual XU. C is equal to T. You can find actual XU, that is equal to 85 mm. Alright. So our neutral axis falls within the flange. That is our assumption, which is proved to be true, right? Okay. So XU is less than DF. DF is 120, so that is definitely true. Now XU should be also less than XU max. XU max is 0.48D, so that is equal to 288. So the section is under reinforced. As the section is under reinforced, so we can use this formula. So the steel which we assumed by using this formula is correct. That is 1864.3 mm square. Okay. Now second case, our design moment is 690. Again saying we know that MUR1, that is, first assumption is that we assume that the neutral axis is the depth of the neutral axis is equal to the DF. That means that the neutral axis is at the bottom of the flange, right? For that we know we have already calculated MUR1, that is 522.79. But our design moment is greater than this. That means that neutral axis falls in the web, right? MU is greater than MUR, so that why XU will be greater than DF. So we will have to make another assumption that 3 by 7 XU is equal to DF. That means that the strain 0.002 falls at the bottom of the flange. Okay. So that means you will have a stress diagram like this. Okay. That means we are taking YF is equal to DF, that is our case 3. Okay. Now we have to check whether this is correct or not. Okay. So when your when the neutral axis is, see, the neutral axis is in the web, right? Neutral axis is falling in the web, but the strain 0.002 is at the bottom of the flange, or you can say this YF is equal to 3 by 7 XU, or you can say DF is equal to 3 by 7 XU. That is why your stress diagram will be here, will be equal to like this, right? So find the moment of resistance, that is MR2. Simple. This is force C. This is applicable to this and this. So this and this, and in between for the rectangular section you would apply this, right? Fine. So C1 is known to us. C1 is nothing but it is 0.447 FCK into YF into BF minus BW, and C is 0.36 FCK into BW into XU, right? Fine. So our moment of resistance will be C into this lever arm. Lever arm for rectangular section, we know it is D minus 0.416 XU. Lever arm for this, we know it is going to be D minus YF by 2. Okay. So C, this is force C, this is lever arm, so this is lever arm, plus this is C1, this is C1, this is lever arm, this is lever arm, right? So from this we get MUR2 as 746. Okay, but we see that our moment is less than this, right? That means 3 by 7 XU is less than DF. That means our strain 0.002 falls within the flange. So our assumption is wrong. Okay. So this becomes case 2. MU is less than MUR2. Hence 3 by 7 XU is less than DF. So this case falls away like this. In this case, that is case 2, right? Over here, your YF will be less than DF. Okay. So now we have to try for this case and find your moment of resistance. Okay, so YF in this case has to be taken as 0.15 XU plus 0.65 DF. Okay, this is your YF, and this should be less than DF, right? So this is applicable to flange, and this middle portion will be this, right? Okay. Okay, so now you can convert this YF into this, that is 0.15 XU in plus 78, because DF is 120, 0.65 into 120 is 78, right? Now we know moment of resistance is C into this lever arm. Okay, this lever arm is no, that is for rectangular section, that is D minus 0.416 XU. The lever arm over for here will know is D minus 5 by 2, D minus Y by 2, right? So this is C. So this is C, 0.36 FCK BWXU. This is lever arm. This is lever arm. So C into lever arm plus C1 into lever arm. This is C1, right? 0.447 FCK BF minus BW into F5 minus, sorry, into lever arm. This is lever arm, right? Now YF you can replace by this, okay? Now design moment we know it is 690. Solving this equation we get XU is equal to 237 mm. Now which is less than XU max, okay? That is 288. That is 0.48 D for Fe415 and the section is under reinforced, okay? So XU is 273, XU is 237, sorry, XU is 237, XU is 237, right? So now you can find YF. Once you know XU, you can find YF. So YF is found to be 113. Our DF is 120. So 113 is less than 120. So this condition has been satisfied, right? YF should be less than DF, right? So YF is less than DF. So that's okay. So now simple. Take T is equal to C1. Take T is equal to C plus C1. So T is equal to 0.87 F5. So this is C, this is C1, and this is stress in steel, right? So this is how you get the AST, that is 3618.27 mm square, right? Now third case, your MU is equal to 748, okay? So we've just found that MUR2 MUR2 was 746. Okay, MUR2 was when your 3 by 7 XU was equal to DF. At that time, we got the moment of resistance of the section as 746. Now the design moment is 748, which is greater than 746. That means 3 by 7 is greater than DF, right? When 3 by 7 XU is greater than DF, so it will be case 3, right? That is the strain point 002 falls in the web, okay? So instead of YF you will take as DF, okay? So your YF will become DF. So that is why your lever arm will be D minus DF by 2, okay? So again same case, very simple, okay? Find mu, that is C into lever arm plus C1 into lever arm. So this is C into lever arm, this is C1 into lever arm. Okay, you know your mu, that is 748. Okay, so you can find XU solving the solving this equation. XU is found to be 282.19, which is less than 288, that is 0.48 D in case of Fe415, that is your XU max. So the section is under reinforced. Again, take T is equal to C plus C1. Okay, T is equal to 0.87 Fy AST. So this is C1, this is C, this is C1 divided by stress in steel. So you find the steel area is 4002.77 mm square. Okay. Now let us design the T-beam as a balanced section. So we know for XU limit by D for Fe415 is 0.48. So that turns out to be 288. Okay, you have to find the limiting moment when your XU limit is 288. Okay, so first check 3 by 7 XU limit is 123.42, which is greater than TF. So it is a case of case 3 where YF is equal to DF. Okay, so take C into lever arm plus C1 into lever arm. This is C into lever arm, this is C1 into lever arm. Over here YF is equal to DF, right? So you have to replace YF by DF. That is the only change. Okay, simple, very simple. So you find your mu limit as 751.75. Then you can find your steel, that is T is equal to C plus C1. This is C, this is C1. AC limit divided by stress in steel, that is equal to 4031 mm square. So very easy, right? Okay. So I hope you must have found this video useful. Please visit website mmsprogramcivil.com for all the education videos and its PDF. Please watch the following videos uploaded on the website mmsprogramcivil.com for solved example. Step-by-step design of singly doubly T-beam and bearing depth of 3D frame part 1 and part 2. This is video uploaded on my website. You can watch this, which is further extension of this video, right? Okay. So I hope you must have found this video useful. Thank you.